Hi Bobcats. In this video, we're going to step away from the math for a few moments and look at something known as Le Chatelier's principle. This is a principle that guides us to shift the equilibrium in the direction that we need it to go. For instance, if you have a commercial process that's a reaction that reaches equilibrium instead of going to completion, you may want to do things to optimize the reaction so that you get as much product out of it as you possibly can. Le Chatelier's principle gives us some guidelines about how to shift the reaction one way or another. Our objective is to identify the reaction conditions that shift the equilibrium position of a reaction. Le Chatelier's principle is all about restoring balance. If you have a system that is already at equilibrium, and then you do something to mess with it, for instance, you might change the temperature, or you might add some more reactant. Well, as a consequence of that change, the reaction will either proceed in the forward or the reverse direction until it reaches a new equilibrium position. The direction that it goes is trying to counteract the disturbance that you created. Most of the time, Le Chatelier's principle is talked about in terms of shifting the reaction to the right or shifting the reaction to the left. So what do these phrases mean? Shifting to the right means that the reaction will go in the forward direction, so it will make more product. It'll use up more reactants. So going in that forward direction is usually referred to as shifting to the right. If the reaction shifts to the left, the reaction will proceed in whichever direction, or it will proceed in the reverse direction, and that will make more reactant. It will use up some of the product, and that's just going in the reverse direction. So let's see what happens if we change how much of a reactant or a product is present. So in the first bullet point, it says if reactant is added. Okay, so let's imagine for this equilibrium reaction down at the bottom that we added some nitrogen. Well, if we add some nitrogen, we just messed up our equilibrium. We now have too many reactants, so the reaction has to go in the direction that will use those up, get rid of them, and convert them to products to reach a new equilibrium position. Well, that means that the reaction will go in the forward direction, or it will shift to the right. So adding a reactant will shift the reaction to the right. Now, the next one says, all right, what happens if we add a product? Okay, so that would mean in this specific example that we added more ammonia. Well, if we add more ammonia, now the numerator of our Q expression is bigger, and so Q is bigger than K, and so the reaction will have to go in the reverse direction to convert some of that ammonia into nitrogen and hydrogen until we reach a new equilibrium position. So the reaction will go to the left. It will go in the reverse direction. Okay, let's take a look at the next one. The next one says that we are going to remove product. So that means that we're going to take away some of this ammonia. If we siphon off some of the ammonia product, then the equilibrium will go in the direction to try to replace it, which means we're going to make more product, which means the reaction will go in the forward direction, converting some nitrogen and hydrogen into ammonia, or the reaction will shift to the right. And last but not least, we are asked to remove some reactant. So let's say we take out some of the hydrogen gas. If we remove some hydrogen gas, then the reaction will try to replace it. And the way that it can replace it is by decomposing some of the ammonia into nitrogen and hydrogen. So the reaction will shift to the left to try to make up that reactant that was removed. Some Le Chatelier's questions don't ask you about shifting left or shifting right. In other words, they will ask you about a particular chemical, and does the amount of that chemical increase or decrease as a response to the change in the equilibrium. So for instance, for the first bullet point, if more nitrogen is added to this equilibrium, what happens to hydrogen? Well, nitrogen is a reactant, and we are increasing how much of that reactant is present. And so if we add nitrogen, the reaction will go in the forward direction to use up that nitrogen and create more ammonia. And that means that the nitrogen has to react with the hydrogen that's already present. So as that hydrogen reacts, its amount will decrease to give us more ammonia. So the amount of hydrogen will decrease. Okay, let's erase those, and there we go. Now take a look at that next bullet point. If more nitrogen is added, the concentration of ammonia will, well, as we added more nitrogen, the reaction proceeds in the forward direction to try to eat it up. So that means we're going to make more ammonia. So the amount of ammonia will increase. If ammonia is removed, so we're gonna somehow get rid of some of the ammonia that's in our reactor, the concentration of hydrogen will, well, if we remove ammonia, then nitrogen and hydrogen will react in the forward direction to produce more ammonia to counteract that change. So that means that the amount of hydrogen will decrease as it reacts to give us more ammonia. And let's see, get rid of those marks. And last bullet point, if ammonia is added, the concentration of hydrogen will, okay, so if we add more ammonia after the system's already at equilibrium, the system will respond by trying to get rid of what we just added. And so that means that the ammonia will decompose, the reaction will shift to the left, and as it decomposes, the amount of hydrogen will increase. So that's just an alternative way that Le Chatelier's principal questions get asked. They'll focus on just a single chemical and say, hey, if you do this to mess up our equilibrium, what happens to this one chemical? When I first learned about Le Chatelier's principle, I was a little perplexed by the concept of removing a chemical from the reaction. I got the idea that you could always add more stuff to your reaction mixture, but I was thinking in terms of beakers, and if you have stuff dissolved up in solution, how do you get it out? And that just didn't make any sense to me. Well, for something like the Haber process, I can actually show you how you could remove ammonia from this system. All of these chemicals are gases, and this kind of complicated interconnected reactor system is used for the Haber process. So you can start over here in the upper left by feeding in nitrogen and hydrogen to start reacting them to make ammonia. That happens here on the left in this first reactor. There's a catalyst, and as these gases feed over the catalyst, they'll react and turn into ammonia, but it's in equilibrium, so it's not completely turned into ammonia. So you'll see up here coming out of the reactor is the ammonia plus unreacted nitrogen and hydrogen. So it will this mixture of gases goes into this heat exchanger, and in this heat exchanger, the uh, ammonia can get cooled down. Actually, all of these gases will get cooled down a bit, and then it continues on through the heat exchanger to another container here, another reactor that's labeled a condenser. The purpose of this is to condense ammonia. Ammonia has a much higher boiling point than either nitrogen or hydrogen. So if you start cooling this to where it is below the boiling point of ammonia, but still above the boiling point of nitrogen and hydrogen, then ammonia will condense out, but nitrogen and hydrogen remain in the gas phase. So as the gases pass through this condenser that's really, really cold, the ammonia will turn into a liquid, and you can just use gravity to feed the ammonia into this chilled unit down at the bottom. Now, nitrogen and hydrogen are still gases, and so they get caught and they get sent back into this heat exchanger, and then they get heated up in the heat exchanger, and they get sent back into the main reactor to have another pass through the catalyst to try to convert them into ammonia on that next pass. So by using the higher boiling point of ammonia, you're able to condense it out, preferentially over nitrogen and hydrogen, and effectively remove it from your equilibrium mixture. That then will shift the equilibrium to give you more ammonia. Our objective was to identify the reaction conditions that shift the equilibrium position of a reaction, and in this video we took a look at how changing the amount of a reactant or a product could do that. The equilibrium reaction will respond in the direction that counteracts whatever you did. If you add a reactant, it'll go in the forward direction to use up that extra reactant. If you add a product, it'll go in the reverse direction to use up that added product. And then if you remove a reactant, it'll go in the reverse direction to recreate the reactant. If you remove a product, it'll go in the forward direction to give you more product.